phase transition, then you see some interesting features happening there, and that's what I try to describe towards the. Okay, so as we all know, black hole research in black holes has been a very fascinating area to work in. Ever since Hawking gave the temperature proportional to 1 by m, and this of course, for a simple Schwarzschild black hole, this of course signals some instability, because as the mass keeps on decreasing, the temperature goes up. Okay. And then of course there are several other works, but just to point out one more work by Penrose, much before that, regarding the fact that the mass of a black hole can also decrease if when rotational energy is extracted, because when rotating black holes, they generally have an ergosphere, and you can have in that region, you can have a particle going in and coming out and extracting some energy from the rotational energy of the black hole. And once the rotational energy or the angular momentum goes to 0, the black hole of course becomes a Schwarzschild black hole. But then of course after that there was a proposal that the area of course should never decrease in any of these processes, and then we had this famous Bekenstein-Hawking result. Okay, so
why do you say that negative specific heat is an instability?
Well, ultimately it's going to radiate away, and there will be no thermal equilibrium.
So suppose we had a small black hole in global ADS.
Right.
That would be stable, right?
As long as it's, you mean the small black hole radius is smaller than the ADS length scale?
Yes, smaller than the Hawking, smaller than Hawking page transition scale black hole.
Right.
If we let it evolve in time, as you say, the radiation will go hit the boundary, fill up the space between them, and then lead to an equilibrium between the radiation outside and the black hole.
But at a given temperature?
No, but not at a given temperature.
Okay.
In time.
In time, you are saying?
Yes. I put the small black hole there, I have ADS, and I'm not allowing you to take energy in it.
Okay.
Time evolution, I think, will just end up in the small black hole. Is that wrong? Is it dynamically an instability? Or is it thermodynamics?
So it's a it's a static situation. We are talking about instability from the static point of view. What you're asking is a dynamical.
Yeah, I'm asking if I have such a configuration, I mean, can it be the endpoint of a physical system? Is there something that tells you that can never be the endpoint?
So this description is based on the canonical ensemble, right? Where you actually talk only about the equilibrium. You fix an equilibrium temperature and then you ask this question.
Okay, so I agree that it can never be it's not a stable saddle point for that question.
Right.
Suppose I'm interested in the microcanonical ensemble, evolution in time. Configuration of the system that under time will be fine.
Okay. I'll definitely, thanks. Think about it. Okay, so the first law of black hole mechanics, what you do is you generally associate the internal energy to the mass of the black hole, and then gives you the relation du is equal to TdS, and the instability which we just pointed out turns out to be the negativity of heat capacity, which just comes from this taking derivatives of this internal energy. Okay. You can have, of course, other couplings. You can have charges, and you can have other gauge couplings, and then you can write down a generalized first law. So this is angular velocity, angular momentum, potentials, and so on. Okay. Still, the question, of course, remains that where do you have this? Why we do not have a PDV kind of a term which comes from the pressure and the volume, which we generally have in thermodynamics. Okay. But before you answer that question, where is the pressure and volume, you will of course have to answer how do you associate a volume to a black hole, right? So the trivial thing to do is you want to associate a volume, you just take the horizon, you start integrating from 0 to the wherever the horizon ends, and that will give you the volume of the black hole, right? So naively one can of course define that this, you would think of it as volume of the black hole. Of course there are problems. One problem is that inside the horizon the radius vector, I mean it's time-like, so you don't know what your When you say you're integrating, you don't exactly know what you mean by this integration. But for the moment, if you think of it as defining like this, then the internal energy would have to be a function of both the entropy and volume, two independent variables. And momentarily, in a moment's thought, you can check that entropy, of course, is pi r square. So there is already an inconsistency that entropy and volume are not independent. So your internal energy cannot be a function of both temperature and, both entropy and volume. Okay. So this probably was one of the reasons why volume was not integrated into this picture. So possible one resolution which has.
Sorry, if you, that R square VR formula,
Yeah.
that of course is a flat space form. So, I mean, if it is like some very large black hole in ABS,
Yeah.
then the formulas would be significantly different, and eventually the growth of both the volume and the area would be similar.
So here you are thinking of essentially just thinking of a sphere and integrating it from the origin just to get the volume of the sphere. That is all you are doing here.
In what sense is that a volume? That's what I mean. We're doing GR. So in some kind of root G, we have to integrate.
Root G should also, in principle, root G should also be there. So this was just suggestive. We'll just come to.
I mean, there is another dimension in the game, which is the ADS radius. Let's say. If it was, or whatever, it's some other kind of space time other than flat space.
So we just take a sphere. I mean, horizon. How do you?
No, the only thing that we can say is that it would go as a cube of a length.
Right.
But if there are other length scales in the game,
Right.
then it could be RH square times that length. Just
Okay.
as a possibility.
Right. Okay.
If there are other length scales, then you can't say that it will go as RH cube, right?
So correct.
RH cube times some dimensionless ratio
Correct.
of RH and RADS.
Okay.
That's the
Okay. Yeah, so one possible resolution for this, which has gained a lot of momentum recently, is that you could associate a thermodynamic pressure. If you have a cosmological constant in your theory, you could associate a pressure which is negative of the cosmological constant. One issue with this is that there is of course strong evidence that the cosmological constant is tiny and positive, but if it is positive, there are again certain issues one will have to deal with. One of course is you will have a negative pressure, and that will of course also be some kind of thermodynamic instability. It's not a very big problem, you could deal with some instability, but then there are also other problems in de Sitter space. For example, you have two horizons. One of course is the black hole horizon, and you also have a cosmological horizon. And there are some issues, at least whatever I read, there are some issues in defining mass and other things and asymptotics in de Sitter space. So these things are not, at least to me, I don't understand. So for the time being, what we'll do is we'll restrict to the case where the cosmological constant is negative. And in this case, of course, there is a we have ADS CFT as a good tool to use in this case. So, and think of, in addition, think of the cosmological constant not as a constant. So when you say it doesn't look good, so think of it more like a thermodynamic variable which you can vary. Okay.
The stretched rubber band has negative pressure, doesn't have an instability.
Yeah, so that's not a very big problem. This instability is not a very big problem. It can be dealt with. But there are of course other issues. So you restrict to the lambda less than 0. But of course, even the de Sitter space case is definitely more interesting. I mean, it's very interesting. Okay.
So can you explain once more? I missed what exactly is the issue? What was the issue that you are trying to solve? Sorry, can you just?
So issue we are trying to solve is we are trying to associate essentially we are trying to find an internal energy or some kind of energy which can also include, in the first law, you could also include some kind of a pressure volume term in the first law. Like generally when you want to extract mechanical work, not heat, mechanical work, you generally have a PDV kind of a term. So you are looking to have such kind of a term in the first law. But there is no natural candidate for pressure. So the usual pressure which you talk about in Einstein equations is corresponding to some fluid with some pressure, okay? But that's not what we are looking for here, okay?
And sorry, why do you want this? I'm missing the point, sorry. Why do you want to include a PDV term? What was wrong?
Nothing was wrong. I mean, if you include, you could, for example, extract some mechanical work from it, right? You could extract some energy from it, for example. Suppose you want to, under quotes, you would want to extract some energy from a black hole. Like a rotating black hole, you would want to extract some energy using a Penrose process. So it would be nice to have such kind of a term from which you can extract some energy. So that's the idea.
So in a rotational case, you have the PDV term.
Yeah, I'll come to it. Rotational case, I'll just come to it in a moment. You don't have, right now you don't have, right? You have, for a rotating case, you would have something like an angular velocity and angular momentum. You will have this term, but you don't have any pressure volume term, right? So that's what we are trying to, okay. So this proposal, of course, is not new. It was, I mean, there were a lot of papers, and I just listed just a few of the older papers by these authors, and then there were also some recent works. But the concrete proposal, of course, came in 2009 from Castor, Ray, and Trashen, and some works of Dolan. And the proposal is as follows. So if you think of treating the cosmological constant as a thermodynamic variable, generally, of course, when you solve the Einstein equations, you think of it as a constant and you solve it. Okay. So we'll come to it later what exactly it would mean to actually consider a variable cosmological constant. But for the moment, if you think of it, then what these people showed is that the Smart relation in ADS turns out to be the correct. I mean, dimensional analysis requires a variable cosmological constant. You get the correct Smart relation in ADS. Okay. And the other proposal is that you identify mass of the black hole not with the internal energy, but you identify it with the enthalpy of the system, which people generally study in chemistry. So enthalpy is, of course, U plus PV. For the moment, we are putting both S and V as thinking of it as independent, and we'll go ahead with this identification. And if you do this, of course, then in this case, you have, if you have a black hole has some volume V, then the energy is EV, and that internal energy will turn out to be M minus PV. So in this case, because of this negative sign, what you could think of is, if you have an empty ADS space and you want to have a black hole, then you cut out a region of volume V from that, and you identify that volume with the geometric volume of the black hole. So this is one of the proposals. There are actually several other proposals. Parikh had some other proposal, and a few others had, but this is one of the proposals we'll go ahead with. Yeah. So you think of this volume as a naive volume, essentially, as in the sense of what we were describing before. So you cut out some space and you want to put a black hole in that. So whatever is the area of so you have an area of the horizon multiplied with appropriate powers of R, and you get the volume. So you call it the naive geometric volume. Okay. But once you have enthalpy in the system, you could also get volume from thermodynamic relations. Okay. So you could take dH by dP, and you could calculate the volume from here directly from your enthalpy, and that you can call it as the thermodynamic volume. A priori, there is no reason for these two volumes to agree, thermodynamic volume and the geometric volume. They're computed in a different way. But of course, if you do that, then of course your first law gets extended, and by legendary transform, you have the mass which is identified with enthalpy, and you get this new first law. So if you put angular momentum to 0, these equations actually appeared in some of these older works, and also in the work by Padmanabhan, when unfortunately some of these works are not well cited, but it already appeared here. Only thing is the interpretation was not given, what it would mean to have such kind of a way. So VDP term already appeared in these works, but no interpretation was actually given. Okay, it was included for some other reason. So now, so this is actually called extended thermodynamic phase space because now you have pressure which comes from the cosmological constant and its conjugate volume which you have introduced. This is the two new things you have introduced, and this particular thermodynamic description is called extended thermodynamic phase space, as opposed to the old one where these additional terms were not there. So lot of work has been done, and I'll just mention just a couple of them. These were some older works by Chamberlain, Emperor, Johnson and Myers, where they studied the phase transitions of charged black holes in ADS, and they showed that there are first order phase transitions and which end in a second order critical point and so on. But once you include the PDV term, it turns out that the analogy between phase transitions in charged black holes in ADS and the liquid gas system described by the van der Waals equation, the analogy turns out to be complete and correct, including the matching of critical exponents as well. Okay.
I just want to understand this enthalpy. I'm not familiar with the concept.
Even I was lost actually when I.
So what is it? Free energy minus P?
Right, right.
So should I interpret it as the free energy that the system has over and above what it would have had if all of the system was occupied by the heat bulk?
Correct. Yeah. Yeah. Perfect.
So then this additional term,
Yeah.
EV term,
Yeah.
is it like if I was doing a Euclidean path integral, then the black hole geometry, yeah, so it will have some lambda root g integral.
Yeah.
So what I'm saying is that the lambda root g integral in the Euclidean space-time will stretch from the horizon to infinity, obviously, because the Euclidean guy does not see the inside. So it just becomes like a lambda times the excluded volume, the volume that
Volume that you would exclude.
Is that the reason why the lambda turns out to be like the conjugate thermodynamic conjugate variable to integral?
You mean when we are calculating the Euclidean path integral for this?
Yeah, if you write the Euclidean.
That I don't think you touch. You calculate it. So even if you didn't have this term, you calculate the Euclidean path integral as it is. But this is something extra you are adding. I don't think it appears, at least the Euclidean path integral has not changed from what I have checked.
Euclidean path integral as such, yeah, would include the lambda root g.
Right.
So that would have been free energy.
Right, correct. That is the free energy, correct. So at that stage, you are not actually thinking of lambda as dynamical at all. You are not doing that. Probably it is not, I don't know, probably it is not right, but you are not doing that actually. You are keeping it as a constant, calculating your Euclidean path integral and getting the free energy from
If
there.
I differentiated the Euclidean, if I differentiated the log of the Euclidean path integral, I would have, with respect to lambda, I would have got integral of square root g.
Correct. Correct.
But that's not this kind of stuff.
No, that's not this kind of stuff. Yeah, that's not this. That's not what you are doing here.
And just to say again, so the free energy we understand, it's the Euclidean path integral, Euclidean action, let's say classically, of the black hole.
Right.
And this enthalpy you're saying is this free energy plus what? Plus lambda?
Plus an additional term.
And what is that additional term? It's lambda. P was identified with lambda?
P was identified with lambda. So do we?
Something you put in?
So P is this minus lambda by 8 pi. This is your P.
Okay.
And you postulated that it has a conjugate V, and that V can be calculated. Once you know the enthalpy, you can calculate the conjugate from there.
But how do I know the enthalpy? What is the enthalpy again?
We'll just come to it in a moment. So enthalpy is just mass of the black hole.
Enthalpy is
We identify the enthalpy with the mass of the black hole. You can calculate in terms of other thermodynamic variables. You just invert it and you will get the enthalpy from there.
Sorry, what is the relationship between internal energy and mass?
So generally what you do is you identify, if you are looking from the dual point of view, dual field theory point of view, you identify the mass with the internal energy. That's the general story.
Yeah, if it's a black hole just sitting there, it will be the same, right?
Right.
Okay.
But here we are saying that instead of identifying it with internal energy, identify it with enthalpy. We are saying that is more natural. That's the only difference. Big difference, but.
You're saying even for a black hole that's just sitting there, there's one more source of energy. That's not just mass.
Right. Right.
Some more is,
So if you include this, then so if you look at, yeah, that is correct. That is correct. Yeah. So you have the PV term as well. That is correct. This turns out to be very useful in chemistry. So, but so that's why people started calling this black hole chemistry. So people are writing papers with the title black hole chemistry. So okay, let me just go ahead a bit. Let's take one example to see how this actually works. So the standard Schwarzschild black hole in ADS, you can calculate the entropy and you have the pressure and the mass is explicitly known. So what you do is you identify this mass, you postulate that this mass is actually enthalpy, okay, and rewrite your RH. RH of course can be written in terms of entropy and the cosmological constant in terms of pressure, and you get this relation. So this becomes now your starting point. This enthalpy becomes your starting point now. Once you have the enthalpy in terms of pressure, you can of course take a derivative with respect to V and P, and you can get the volume and you can also get the temperature. The temperature which you got agrees with the old definition of temperature. There is no change in it. But you get the volume, thermodynamic volume, which incidentally turns out to be of course 4 pi by 3 RH cube. And here the thermodynamic volume turns out to be same as what you would call as naive geometric volume, and also volume and entropy are not independent, they are related to each other. So if they are related to each other, then you cannot talk about internal energy, because internal energy cannot be a function of two variables which are dependent on each other. Okay. So maybe that's the reason why this was probably considered a bit inconsistent to have cosmological constant as pressure, and probably that's why it was not well studied. But it turns out that this equivalence of volume and entropy is actually very specific to static black holes, and the moment you include rotation, they turn out to be completely independent. Okay, and that one can quickly check that. So this is a rotating black hole in ADS, and here the enthalpy turns out to be slightly more complicated. And once you calculate the thermodynamic volume, what you note is that the thermodynamic volume turns out to be something like this, and unless J equal to 0, and of course just for the moment if you put Q equal to 0, only in that case volume and entropy are related. If you have rotation in your system, then volume and entropy are not related to each other. You can actually go ahead and check what is the connection between the naive geometric volume V0 and the thermodynamic volume, and you notice that the thermodynamic volume computed from the enthalpy turns out to be a bit more than the naive geometric volume. Okay, it turns out to be J square by M, a bit more, and this actually violates the isoperimetric inequality, which actually states that if you take a curve and if you take a closed loop, then the area of that curve divided by the volume has to be the lowest for a sphere or a circle in 2 dimensions. Okay, so that's the isoperimetric inequality. But in this case, what happens is, because the volume is little bigger, if you take surface to volume ratio, this is going to come out to be smaller than the naive volume occupied by a sphere. Okay, so this actually satisfies what is called a reverse isoperimetric inequality, but this inequality is saturated if you put angular momentum to 0. That's for a Schwarzschild ADS black hole. Okay, so this was some work done by Svetich and company some time back.
So you come to this, but just in the dual field theory interpretation, lambda and r always appear in the combination lambda times r. So saying as a function of lambda is same as saying as a function of r. Right? The size of the sphere in which the field theory is located. So I just wanted to understand this something good is happening here. This relationship, whatever your thermodynamic relationship working when you interpret energy as enthalpy and lambda as pressure. I want to know whether that was obvious from a field theory point of view if you replace lambda by 1 by r. Is this something that...
Lambda by 1 by r.
Because I think lambda times r is changing lambda and keeping r fixed, I think it's the same as keeping lambda fixed and changing.
Yeah, two different ways of, two things you could, true. That is correct actually. You could do that as well.
In the field theory, there's no lambda, but there is an R.
In the field theory, there is N actually. So
But suppose we just do, oh, you're saying that changes Newton's constant.
right. Well, that is one way to do it, correct. Yeah, change the Newton's constant. That's one way to think about
I
it.
see, thank you.
Okay, so let's go ahead with this. And so Dolan actually did some small computation. What his thought was, suppose if you take one can interpret the Penrose process in the following way. You take a black hole of initial mass m with some internal energy and take it through a quasi-static process in thermodynamics. And if there is the final energy turns out to be less than the initial energy, then you would be able to extract some energy from the black hole. Okay. So one could actually think of computing the efficiency of this process, and the efficiency is just standard given by, so what I am giving you is maximum efficiency. And so what you mean by efficiency is you take so when we say U initial and U final, U final turns out to be the maximum angular momentum possible, and U initial is when the angular momentum is set to 0. So this is the maximum energy you can extract from a rotating black hole. Okay. So this turns out to have this following relation, and if you just put lambda equal to 0 in this, then you of course see that all the pressure terms drop out, and it's just 1 minus 1 by root 2, and that gives 0.2929, which was the old result of Penrose and Wald and others, where they said that if you have a black hole of mass m and with some angular momentum, the maximum energy you can extract is actually 29% of the mass of the black hole. Okay, so that you just recover that in the case when lambda is 0. But if lambda is non-zero, in particular negative, the efficiency actually goes up to 0.5 times something. Okay. So negative cosmological constant aids you in increasing the efficiency of a Penrose process.
Let me understand this a little better. What does extraction of this energy? Are we in ADS or flat space? Or
ADS.
ADS. What do you mean by extraction of energy? What does it mean?
What you mean is that you are going to shoot a particle, let's say, and the particle can, let's say, pair produce in the ergosphere, one of which probably goes inside and the other can, so mass energy relation, one of them can actually come out with slightly higher energy, and the angular momentum of the black hole can reduce a bit in this process.
So extraction of energy means take energy out of the black hole into something outside.
Right, that's correct.
And okay, so you are asking what is the maximum fraction of the by internal energy, is it just mass or something else?
So internal energy is just mass.
So what is the fraction of the mass that you can extract out of a black hole?
Right.
And I should be able to answer this by the area increase theorem?
Right. Yes.
Fine. So
Yes.
I do some process such that the area does not decrease.
Right, correct. And you extract, yeah, correct. That's okay. So now let's ask a slightly more general question. Now that we see that there is some increase in the efficiency, one can actually go a little full-fledged and talk of our usual high school heat engines.
And this maximum efficiency, is it achieved for large black holes, small black holes?
Angular momentum, if you have, because once the angular momentum is 0, you don't extract any more energy. So you would want to have a very high angular momentum.
I understand, but you want to be different from flat space to get this more increased efficiency.
Correct.
So you want your black holes to be large in ADS units?
For increased efficiency, you are asking.
If you've got a very small black hole, it shouldn't make a difference that you're in ADS.
Actually, it will turn out that the efficiency is the difference of masses. So let me go ahead. We'll just come back to your question in a moment. Yeah, we'll just come back to it. So here, so we can now ask a question. Now that we are talking about a quasi-static process of something like a thermodynamic heat engine, where you start from some equation of state, you define a closed path in the PV plane, and if the amount of input heat is QH and amount of output heat, so the usual PV diagram which we have. Okay, so you have this isotherms. And these are at constant temperature, isotherms. So you can pick a point, okay, and you can go through steps 1 to 2. And there, this of course will be your adiabatic process, okay, where the temperature of course jumps, but there is no net heat, and you go back through this cycle. Okay. You can call this as TH, the high temperature. Okay. This kind of a thing will be possible because now you have a PdV term in your first law.
So when you talk about extraction of energy, you don't mean in a real possible physical process in a fixed radius?
Well, for the if you don't have rotation, then I do not know actually whether this really corresponds to extraction of energy. But when you have rotation, in that case, because entropy and volume are independent of each other, there is a clear-cut physical interpretation that you could actually extract rotational energy from the black hole.
Sure, you can extract energy. I just want to understand the point. When you claim that there is some efficiency possible,
right?
Are you claiming there is a genuine physical process?
Genuine physical process, because see, if you let's take a black hole with certain angular momentum j, and thermodynamically, let's say the j decreases because of your particle, which takes away extra energy, okay? And but you can perform a cycle, complete the cycle, go back to the initial. So
this cycle, by genuine physical process, I mean, for me, lambda is a constant. I don't want to change it, but in a physical process. Now you can do that in some thought experiment.
Okay.
But in the end, I mean, you should be
true.
For me, you should be telling me what you can do at a fixed lambda.
True. Then this will not work. Yeah, at a fixed lambda, this won't give you any answers. Yeah. Right. I agree with you actually. Yeah.
So you are saying that you may not be able to extract so much energy sitting at fixed lambda.
Sitting at fixed lambda. No, it won't work.
Okay.
Yeah. So in that sense, it will be unphysical as well to ask this question probably.
Or maybe, you know, there's context in which maybe it's physical, but
yeah.
In the usual context.
In the usual I agree. Yes.
You're sitting at a fixed P.
Yeah.
I mean, then you can't draw this actually. I mean, you're always at a fixed P.
Yeah, but I was wondering that maybe this is some technical device to get some number, but that number could actually be achieved by
Even
staying at. Meaning, it's certainly true that you can extract energy from rotating black holes, even in the sense that I'm calling this. For instance, a black hole can become super radiant.
Right.
It can emit
Right.
energy. So, for instance, that would be a question. Suppose I have a super radiant black hole. We know exactly how much energy it emits because we know the instability endpoint.
Right. Yeah.
Actually, we don't. But okay. Okay. At least you can estimate. I mean, I was just wondering whether that.
You can estimate. I mean, for that case, you can estimate probably.
And is that the same? Would you get the same fraction from there as from here?
If you keep lambda dynamical, one can definitely try.
No.
So if you keep it.
A super radiant black hole in a fixed radius. Okay, it emits angular momentum into gravitons. So we don't understand that very well. But let me ignore that. Conceptually, it emits angular momentum into gravitons. Certain amount of the energy comes out. The final black hole is a black hole in which some fraction of the energy is in gravitons outside. So some fraction has been emitted. Is that fraction what you would associate with this efficiency here, or not, or something else? I think a real process would be hard to do better.
I see. I'm just trying to think actually if I have used anywhere variable lambda to get this computation. That's all.
So this 29% was what calculation? The before?
Before. Just put lambda equal to 0.
What calculation was that? What did the calculation? What gave you?
That was the calculation where you do this particle scattering. Send a particle at the ergosphere and try to compute.
You keep doing Penrose processes.
Right. That's right. So that's that old calculation. This is not what Penrose said. Of course, this statement is not what Penrose said. Penrose calculation was different. But this is like in this situation, in this setup, you could think of this as a Penrose process. Only thing is because if you think of a heat engine, you have to complete the cycle again. You have to come back. Okay. You have to come back through a series of quasi-static slow steps so that you are still close to thermal equilibrium. You have to come back to your original position, original point in your cycle. Okay. So this is from thermodynamics, that you could extract some energy and you could talk about some efficiency as work done by QH, and this is the standard formula, QC by QH. Okay. So one can think of an engine like that, and in this case the engine would actually correspond to a static black hole which we are talking about. Okay. So if you think of a simple cycle in the PV, so a simple cycle in the PV plane, then in this case these
So at zero angular momentum, according to your processes, can you extract energy or not?
you can extract energy, but that won't correspond to your physical processes. At least at the moment it is not clear. It doesn't look like it will correspond to any physical process.
Yeah, in a physical sense it would violate the area.
Right, right. It won't correspond to actually any physical process. It would mean something else
So
actually.
it's something totally different.
Something totally different actually. So for the simple case, if you could propose a Carnot engine for static black holes where the entropy and volume are related, then the heat QH, you can QH is at the high temperature phase and C is at the low temperature phase. You could compute the heat because the entropy is written in terms of volume, and you can just check that the efficiency will be Tc by Th. These are standard relations from thermodynamics. Okay. Question is, how do you implement it for static black holes? And so what you do is let's take a simple example of a charged black hole in ADS, and for this case the equation of state can be written down like this. So you have this temperature relation, you can invert the temperature relation, write L in terms of your pressure and R in terms of entropy, and you can invert it to get a equation of state for the black hole. Okay. So this equation of state is actually written down at a particular value of the charge parameter Q. The reason is, if you go back to your first law, here you had this term phi dq. So to proceed, for simplicity, what you do is you fix Q to some value so that this term drops out, and you, for that particular value of Q, for particular value of charge, you write down this equation of state. Okay. And enthalpy of course is can be computed. Interesting thing is, here the specific heat at constant volume turns out to be 0 just from the enthalpy, but the specific heat at constant pressure has some expression. Okay. What this means, specific heat at constant volume being 0, what it means is that, so so this is an adiabatic process where there is no heat. Okay. So in this dq is 0. Okay. What it means is that instead of this kind of a cycle, you could think actually of a slightly different kind of a cycle, which is slightly easier to implement and compute. You could think of a cycle which is just a rectangle. Okay. Something like this. Okay. And think of this as 1, 2, 3, 4. Okay. So if you travel in this direction, okay, then of course the volume is changing, and in this case you are only the pressure is changing essentially. Okay. So if it's if the specific heat at constant volume is 0, what it means is that if you keep the volume fixed, then the entropy is also fixed, and as a result the heat is 0. Okay. The heat generated is 0. Okay. So what you can do is you can actually think of a simple rectangular cycle. So instead of going along like this in isotherms, you can actually think of this kind of a rectangular cycle, and this turns out to be very easy to compute. Okay, because if you look at the upper and the lower lines, heat flow is only around 1, 2 or 3, 4. There is no heat flow along these directions because the volume is a constant. So TdS is 0. As a result, there is no heat flow along 1, 4. The heat flow is only along the upper line and the lower line. So you can use this fact to calculate the work done very easily, and also you can try to compute the heat by integrating over the specific heat Cp at dt. So these computations are not very difficult. You can actually do it straightforwardly, and you can estimate that the the efficiency of the engine actually has a slight expansion, you take a large volume expansion because you don't know exactly how to compute, and you can show that the efficiency actually goes as 1 minus P4 by P1 in our cycle, and that's nothing but V2 by V4. And you see that if you want to achieve the Carnot efficiency, then you should have the Carnot efficiency is 1 minus Tc by Th, you should have V2 is equal to V4, but then if V2 is V4, you can actually check from here that the work done will actually be 0. So the bottom line is that, so this was some work done by holographic heat engines by Johnson, and there he argued that if you want to have efficiency close to Carnot efficiency, then your total work will actually become 0 if you want to exactly achieve Carnot efficiency. So we'll come to the meaning of what these things are slightly unclear as to what we mean by efficiency and what we mean by a heat engine. So we'll come to it towards the end. But let's go ahead a bit, okay, and see how to improve this situation, how to take the efficiency close to Carnot efficiency. So the one clue actually comes from the temperature relation. What you notice is that the temperature goes in terms of entropy, pressure and charge goes like this, and at some particularly large value of Q, the temperature is going to become negative. Okay. But you can avoid it if the entropy also scales as Q square, because in this case the Q squares will cancel and you will have a temperature which is positive. So if you want to take Q very large, charge parameter to be very large, one way to do it is you try to propose that the entropy should also scale appropriately as Q square. And if entropy and scales as Q square for dimensions, you will see that the pressure has to scale inverse of Q square, and that gives you that the temperature actually should scale as 1 over Q. So as long as these scaling relations are respected, you can take the charge of the black hole to be as large as you want, and the temperature will not be negative. Okay, so you can stay in the physical region. What you mean by temperature negative is you start going more and more towards the right, and that becomes an unphysical region for you. Okay. So what is the advantage of doing this? Advantage is these relations, S going as Q square, entropy going as Q square, pressure as inverse of Q square, and temperature as inverse of Q actually precisely happens at the critical point of a second order phase transition. So in this system you have a second order phase transition, and at the critical point, which you can find from taking first and second derivatives of pressure, you can check that at the critical point this is exactly the scaling which you require. So the question is, can you take this engine, not put it in any isotherm, but put it at a critical isotherm? So this is a PV diagram, and below the PV diagram the usual interpretation in thermodynamics is you have a liquid phase, and above a certain Tc you have a gaseous phase, and there is a certain Tc. Okay. So what you do is you try to put your engine, your cycle, whatever we have defined, take this cycle and put it as close as possible to the critical point.
So what is this critical point in terms of the usual things that we know about black hole phase diagrams?
So this is same as the liquid to gas phase transition, right? You have a first order phase transition which as you go on, it ends in a second order phase transition.
Yes, but so you're saying that I have the standard Hawking page phase transition
Right.
phase diagram.
Right.
To that I should add some charge chemical potential.
Right, correct.
And then there is a critical point.
Critical point, right. So this charged chemical potential was what Johnson and Myers did long time back, but now this also turns out to be correct even if you add the PDV terms in your first law and go through the same procedure. Okay. Well, it turns out if you put the engine exactly at the critical point, work done is still 0. One can check it. I will not do it here. One can check it. But what turns out to be interesting is if you can put this engine cycle close to the critical point, in the neighborhood of the critical point. So these are some sample isotherms for a Gauss-Bonnet black hole, and same things you could do it for other charged black holes. Okay. So what you do is you take your engine and put one of the edges at the critical point, okay, and the other edge you scale it to be slightly bigger or smaller. So precisely how you do it is you for example, take P3 and P4. So this is your P3 and P4. You take it to be exactly the critical value. Whatever the critical value is, given a charge, you can find out what is the critical value. But take P1 and P2 to be some integral multiple of P critical, so that the cycle has some kind of a width essentially. Okay. But since P critical scales as inverse of Q square, if you take Q going to infinity, all the pressures are going to go to 0, so the cycle which you have is going to shrink completely. So to avoid that, what you do, you scale the volume also appropriately in this fashion, so that as the pressure differences start becoming smaller, volume differences start becoming bigger, and the engine has certain area, it's not 0. I mean, the cycle has certain area, it's not 0. Okay. And in this case, what you get is that you get a finite work. Okay, the work turns out to be a constant proportional to L at any Q. Okay, doesn't matter what Q is, the work turns out to be a constant, so it's not 0. Okay. And the net heat flow you can compute, you can actually compute the efficiency as well, which is just compute the work by QH, you can get the efficiency. And you know wherever you have fixed one of the edges you have fixed at the high temperature, so you can calculate that point from the critical value of temperature, and you take a large Q expansion of your lower value. Okay. And in this way, you can get a Carnot efficiency. How the Carnot efficiency would go, you can get it, and how your efficiency of your black hole goes. And you can take a ratio of the both and check whether the efficiency of the black hole at the critical point actually approaches the Carnot efficiency or not. Okay, you can draw a plot. And these are some sample plots for 5-dimensional black holes in comparison to Gauss-Bonnet black holes. So upper you have, so the blue curve is essentially for the RN-ADS black hole with charge, and the red curve is for the Gauss-Bonnet black hole, neutral black hole, which has only one Gauss-Bonnet parameter alpha. So this is for the higher values of alpha and Q, and this is for the lower values. So what you see is that at the lower values of alpha and Q, it's the ADS which actually has a lower, if you run the engine with an ADS black hole, it has a slightly lower efficiency. Whereas if you go to higher values of Q and alpha, the ADS black hole dominates with a higher efficiency. Okay, so is there any first of all, any motivation to do this, and what would actually this kind of efficiency calculations, will they mean anything? Because you see, you can take any, so this now is a game which people are playing. You take any static black hole and you start computing the efficiency, but you don't know what it means actually, what to do with that number. So you computed some efficiency, you got some numbers, but you don't know what to do with these numbers. Okay. So this proposal of taking the cycle, thermodynamic cycle, and putting it at the critical point was actually given by Campisi and Fazio in a paper some time back. And their proposal essentially was that if you want, so this paper is essentially from statistical mechanics, it has nothing to do with black holes, and this is for, in general, day-to-day engines. Okay. So if you take day-to-day engines, you want to get a maximum efficiency from your engines. What you can of course do is you can add lot of engines in parallel, and the efficiency of course will go up, but then the number of resources will also go up. So what they suggested was, you could actually get a good gain in efficiency if instead of having a lot of engines in parallel, you somehow let the engines interact with each other, okay, and think of them as some subsystems with some kind of an interaction. And particularly, if these subsystems conspire in such a way that the substance turns out to be at the critical point with some critical scaling of exponents, then you can get some anomalous scaling of exponents, and at that point, you can actually show that the efficiency has, instead of you can actually get a much more gain in efficiency in that situation. Okay. So this was some proposal by Campisi and Fazio, and I just included one slide just for information. So what they proposed is that you could go as close as possible to Carnot efficiency if you have this kind of an anomalous scaling behavior, where this quantity which you see, alpha minus z nu by d nu, you would want it to be greater than 0. Okay. And if it is of course very large, then of course in the large n limit, this thing is going to go to 0 and you will approach the Carnot efficiency. So you actually require alpha minus Z nu to be greater than 0. It turns out in condensed matter literature, you have some materials which already show this behavior. One such material is this dyspronium titanium oxide. Okay. And this material is also of lot of interest because dual Dirac strings and magnetic monopoles and spin ice were actually detected in these materials. So this is one material which shows this behavior. Okay. So experimentally there is actually hope in materials that you could actually achieve, go close to Carnot efficiency if you run the engine when the working substance which is inside is on the verge of a second order phase transition. So the black hole story what Johnson proposed was an exactly solvable model or a toy model for this kind of a proposal. Because in this case, you generally do not have an exactly solvable model. You don't know exactly what is the enthalpy relation. You don't know what are the relations between equation of states. It's all numerical. You don't have any exact relations. But in the case of a black hole, these are all exactly for our black holes. So the black hole can be used as a toy model to mimic these systems, and that's what Johnson actually tried to do. Okay. So what does it mean? What it means is that you think of in some sense n subsystems. Okay. Think of n subsystems forming your working substance of your engine, and think of the limit n going to infinity. In the case of a black hole, what it would correspond to is actually having q subsystems, because we are taking the parameter q to infinity. You think of having q subsystems, and q has dimensions of length in 4 dimensions. And in this limit of q going to infinity, if possible, write a model for q particles which are in some sense interacting in the background of this critical black hole. Okay. If you could write such kind of a model with an appropriate potential and calculate the partition function using the microscopics partition function, somehow that model should explain to you what is exactly happening at this critical point. Okay. Now, at least at the moment, it is not known what kind of a model that would be. It might be some kind of if you think from the dual field theory point of view, it might be some kind of a matrix model of q subsystems. Okay. So what one can think of, do first is take a probe approximation, think of a point particle of some mass and some charge which is propagating in the background of this critical black hole. Okay. So what do we mean by critical black hole? You take the standard metric, and in that metric you substitute these critical values for pressure, entropy and temperature, and from that you can get the critical value of the cosmological constant, and you can also get the critical value of mass, plug them into this relation, and the black hole which you have right now is your critical black hole at the critical point. Okay. Now of course now you can ask standard questions. You could think of a particle of charge E and some mass mu, what kind of an effective potential you would have. This is very simple to think of. Okay. It's not very difficult. This is done even in standard GR courses, you do it. And effective potential of course generates the possible orbits in this critical black hole. Okay. And if you plot this effective potential, so what you notice is that, so this is the radial, for a radial geodesic, this plot is for a radial geodesic. So in the situation where your L is 0, what you find is that there is a certain value of mass to charge ratio, okay, where the black hole, there turns out to be a small local minimum, but otherwise it's an attractive potential. Okay, for some value of charge to mass ratio, in this case it's 1/4, you turn out to have a small local minimum, but for other values it's just an attractive potential. Okay. What it would mean, an attractive potential, what it would mean if you're thinking of q subsystems or q particles, then this potential is telling you that the q particles are bound by this potential. Okay. If they are bound by this potential, then they can locally interact and somehow conspire to give you this high efficiency. Okay. But this local minimum, if you have this kind of a local minimum, that can actually destroy this property of interaction between subsystems, because this may correspond to some kind of condensation happening at a local minimum.
Just
No angular momentum in this story at all. No.
Okay, so so what is this calculation? I mean, in the sense that you have a charged black hole,
Right.
and you are sending some L equal to 0. Okay, so it's a head on.
Head on, right.
And you say that, and you're sending a charged particle towards this guy,
Right.
and for some particular charge to mass ratio of both the probe particle and the black hole.
Right.
So there is a dip in the potential.
Right. Right.
Only for that value? I mean,
Only for, so this is not easy to analyze analytically. So this is like some numerical result that for some one particular value, okay, you have this minimum. But as you, particular means if you can have little more, little less, but it quickly goes away. That minimum disappears once you change this value.
some range.
Yeah.
So now
Yeah.
there's a little bounce state there for the particle.
For the particle, right.
And
So this E, mu by E is the charge to mass ratio of the particle. The black hole charge is here.
so why does it mean that there is some energy extraction happening here, or what does it mean?
So
Now there is no ergosphere or anything like that.
no, nothing, no ergosphere.
You
No.
cannot think in terms of Penrose's processes.
Actually, you cannot think at all in terms of extracting any energy from the black hole. It's not that. It doesn't look like that, at least to me. Especially what the comment Shiraj made. It doesn't look like you're talking, here it doesn't look like you're actually talking about a physical process. Okay. So, yeah, so I understand your confusion. What you're asking is, what should you imagine of this particle?
Yeah, because since now you have come back to a particle kind of picture, I think
Right.
that you would again try to connect it with some kind of energy extraction.
So the idea is that you would expect these particles to be some kind of a subsystem. So if you think of your black hole as the substance doing some work, somehow these particles should be your, if you wish to call it like that, the molecules or the degrees of freedom of the black hole. You would actually want to think in those terms. From the microscopic point of view, whatever degrees of freedom you have, you would want them to have a very strongly coupled system such that as you take Q going to infinity, somehow your the efficiency is actually coming up to be higher. That is at least the picture which Campisi and Fazio proposed. This picture, what they proposed is actually that you have n subsystems forming the working substance at a critical point, and because of that you have this anomalous scaling which comes from the critical exponents, and that actually gives rise to higher efficiency. So in the case of a black hole, we are trying to actually think of having a similar picture. So you have to ask what would be the subsystem, what would be those Q subsystems here of a black hole.
So what does the local minimum signify?
Local minimum will actually signify that instead of the particles having a very strong interaction bound by this kind of a potential, they might actually start forming some small kind of shells or some small condensation, like 10 particles forming a condensate, something like what, so here, yeah, so something like what Gupser and Horowitz, Hartnell, they were talking about, some kind of a condensation happening on the horizon. It might have something to do with that. Okay. In the case of holographic superconductors, what people were doing.
So are you saying this would signify super-radiant instability?
Right. Right.
If you had a field,
Yeah.
was not, so if you're saying you've got a black hole, if you've got a charged field with certain properties, that would be a super-radiant.
Right, right. But for super radiant, how do I see it?
You'd see it by most clearly by calculating a quasi-normal mode and seeing if it has wrong side.
Okay. So we were trying to, our next plan was to compute quasi-normal modes, but not for this reason. We were trying to compute it just because it's interesting to study quasi-normal modes, but that is, yeah, thanks. Right.
This also happens for a small range of even ratios in that.
But typically, as E goes up, E, the charge of the particle goes up, superradiant instability goes up.
Yeah.
So the range puzzles. I mean, I would have thought that the limit E goes to infinity, you would have had more and more superradiant.
That I don't know how to check directly from here, but yeah, I don't know the answer to that right now. Okay, so just to give a small comparison, that in the case of a RNADS black hole, you have this local minimum, but with
Just to understand, the particle and the black hole have same sign charge.
the particle and the right now,
In the situation where you have this.
right. Let's just check. Does it change anything? Yeah, they are coming as a product. So, that I didn't check. If you have a same sign and what would, yeah, I didn't check.
Probably, right? I mean, if they have opposite sign, there's no reason for there to be an equilibrium point. Right? Because gravity attracts and the expectation will attract. However, if you've got same sign, you could have electromagnetic repulsion balancing out gravitation, attraction. And that's
Okay, for the Gauss-Bonnet black hole, it turns out there is no local minimum and you just have a binding potential. Okay, this is just one difference from the standard EDS black hole. Yeah, so I'll just finish. I don't know how time. I'll just be finishing anyway. So what you can do is you can think of a large Q limit in the metric itself directly. Okay.
Q is the charge of the black
Q is the charge of the black hole. Okay, large charge black hole. You could think of a large charge black hole, and of course the first and last terms will drop out in this limit, and you are getting some non-extremal black hole with some horizon at some point.
So large charge, large mass. We're working global ADS?
Global ADS. Yeah.
So large charge and large mass.
So mass is gone now. Yeah, large charge, large mass. That's correct. Yeah, large charge, large mass. Right.
So it's like a black brain.
Right.
Is your solution locally becoming a black brain?
I don't know. We didn't think about it at all.
Okay.
Yeah, but you're right. Large charge, large mass. Yeah, limit. Yeah. So what you can do is you can think of a new decoupling limit here. A decoupling limit in which you're taking the charge of the black hole to be very large, and at the same time you're also trying to go close to the horizon. So this is what you do in the case of an extremal black hole, okay, where you want to relate mass to charge, but at the same time you want to go close to the horizon, and the limits obviously don't commute as well. So there, when you take this double limit of going close to the horizon, at the same time taking mass equal to charge, okay, what you actually get is a ADS2 times an S2 background in the case of an extremal black hole, which of course turns out to have an infinite throat, and that's the reason why the decoupling limit is good and it works very well. Now here you can actually ask the same question. You can try to go very close to the horizon by just redefining these coordinates just like you do it in the extremal case, and you can take the Q going to infinity limit at the same time, but keeping this parameter Q tilde, which is the product of epsilon and Q, to be fixed. So if you do that, the metric turns out to be this, okay, and this metric turns out to be just the metric of Rindler space-time, but not with a product of an S2 but with a flat space. So the Rindler part completely decouples from the flat space part. The cosmological constant is 0 in this limit because the cosmological constant is inverse of L square, and L square was actually scaling in the critical limit as Q square. So if Q goes to infinity, the cosmological constant goes to 0, so you're actually getting some kind of a flat space, but this is not the usual Rindler space you get from a non-extremal black hole. If you take a non-extremal black hole, you go close to the horizon, what you actually get is Rindler coupled with an S2, okay, but this is a decoupling limit, okay. Now this decoupling limit what we have checked this for one black hole, but it works for several other cases as well in this, as long as you have a static black hole and few properties, this decoupling limit seems to go through, okay. But so it would be nice to understand from holographic point of view what this decoupling limit would correspond to, okay. Okay, so I have two slides on speculations, and some of the speculations are actually taken from Johnson's works. So here what we have noticed is that when you take pressure to be a thermodynamic variable, on the field theory side it would correspond to something like this relation that Shiraz was pointing out. So you could think of this as dynamical pressure. You could think of it as a dynamical N from the field theory side. Okay. So it is like somehow, in some sense, some kind of an RG flow between different theories on the boundary. Okay. So number of colors, yes, varying number of colors. That is one way to think of it at least. The other way, of course, is to think of varying the Newton's constant. In fact, Karch and company have at least one work where they tried to do it and tried to give an interpretation of dynamical pressure in the boundary, okay, from the boundary gauge theory point of view. But here we are thinking of dynamical pressure as dynamical N. Okay. So this pressure coming from cosmological constant, we don't think of it as the pressure in the field theory. It's different from that. Okay. So what could actually give rise to dynamical N? What actually could give rise to dynamical N is the cosmological constant you generally think of as starting from some higher dimensional gravitational theory. You think of the cosmological constant as coming by giving vacuum expectation value to some scalar fields, moduli fields, and you fix it at some value, and that gives you one fixed point, and that gives you one theory. One, of course, the highly symmetric point is you just put all the scalars to 0. That may be your radius, pure radius. But you could think of having a different expectation values for your moduli fields, generating different fixed points, and this mechanism what we have discussed could be somehow some kind of an RG flow on the boundary between various theories. Okay. Such kind of RG flows, of course, were well studied in literature, but it is unclear whether what is the connection of that with what is going on at this point. For example, what do you mean by a heat engine and what do you mean by work? What do you mean by going through a cycle, and what actually do you mean by efficiency? These questions, at least, I do not know what is the answer to these questions. Okay. Another way is you could get dynamical N is actually you take the number of these branes, you start increasing the distance between them so that you are in the Coulomb branch, you go to infinity or something like that, or the vice versa, and you could actually get a dynamical N in this case. And some of these things were explored long time back by several authors, which I have given here. One reference I have given here, but this has also been well studied in literature. Okay. Yeah, so I think I'll stop here with these two speculations with, as such, slightly disappointing open questions, because on the gravity side, you could do some computations, you could compute a lot of quantities, but on the field theory side, what it corresponds to is unclear. So in that sense, it's slightly disappointing, but given this connection with the number of colors, it is expected that maybe there is some kind of a dual interpretation which we do not understand, at least at this point. Okay. Yeah, so thank you for your patience.
If you're still connected to ICTs,
There was no big problem.
there's a new problem.
Yeah, they had to leave.
So I presume there will be questions.
So just to answer your question which you are asking regarding mass, you could actually, since you have heat flow only along these two directions, only at the top and at the bottom, you can write your dH as TdS plus VdP. And in this case, the pressure is a constant, so this term drops out and the heat comes only directly from here. So you can actually write simply the efficiency, you can just write, so it's 1 minus QH by QC. You can just write it as 1 minus, and QH is nothing but coming from, so this is just your dQH, and this object is just mass. So this is just the mass difference in some sense, something like M1 minus M2 by M3 minus M4. It's just the mass difference. Efficiency of whatever processes we are doing is just the exact formula actually. So you just evaluate the masses at the four corners and you input and you can compute this quantity. So in that sense is the difference of masses.
Okay, if there are no further questions, let's thank Chandra again.
Thank you.